do something a little bit different, and it's not going to be quite the same as the gas law problems that we've been looking at, but we're still thinking about gases and how they react, what they do. So on the first day of notes, if you remember, we said something about this equation. We said that kinetic energy is equal to 1/2 mv squared, and there were those few videos that you guys watched. Didn't really address it in those videos, but I addressed it, and I said kinetic energy is equal to 1/2 mv squared. So we related that to the fact that if you had a really heavy gas, that's going to move pretty slowly. If you had a lightweight gas, it's going to move a lot quicker. So that's what we looked at in that relationship. So you still need to think about that. That's the main idea behind Graham's law. And Graham's law of diffusion or effusion, and essentially those are the same things. We're just looking at the only difference is that in one of them you're talking about a gas escaping through a pinhole, and then in the other one you're talking about a gas just kind of traveling through a porous medium. So in this case, what we want to do is we want to look at the rates that these gases travel. So here we have a little bit of a derivation going on where we've got our velocities and masses, and we continue on with that derivation until we get to this one right here, where we say the rate of one gas divided by the rate of another gas is equal to the square root of their molar masses. So remember, when we're talking about masses for these gases, we're talking about molar masses, which you would find on your periodic table. And the important thing to remember here, and I'm going to bring this up again, but if this is the rate of gas A, then our molar mass for gas A is in the denominator. If you've got it in the numerator on one, it's going to be in the denominator on the other. So you've got kind of a crisscross effect going on. So that's going to be the important thing we see. There are three different formulas that we're going to look at, and this is one of them, which we just identified. And then there are two others that we're going to derive. So again, the important thing here is that you've got this crisscrossing whenever you're setting up that formula, and that's something that you will have to memorize. Okay, so the first question, it says, how would the equation change? Actually, this is not a question, this is just going through that derivation. How would the equation change if instead of rate, you measured distance traveled in a given amount of time? So let's make ourselves a note that our time is constant. That's what we're going to do here, is keep our time constant, and we want to see how that affects our distance. So when we think about rate, and you guys will do this a lot in physics at the beginning of the year next year, when we think about rate, give me an example of units or formula or something. What's a rate? What is it? Miles per hour. Miles per hour. So you're looking at distance over time. So if we have distance divided by time for one gas, A, all I did was change rate to the actual formula, divided by distance divided by time for B. So I changed my formula around. Everybody needs to be writing this down. Well, that's going to be equal to, I just took this and actually changed it to distance divided by time. Everything on the right-hand side of that equation remains unchanged. We've got molar mass of B divided by molar mass of A. That does not change. Well, in this example, it says that we are keeping time constant. So I can come along here, since those are constant, those do not change. They would be the same for each of those, so they cancel out. So now our new formula becomes D of A over D of B. There is our new formula that we want to bubble in. Make sure we have that memorized. And again, notice it's just like formula number one, where you've got that crisscross. So if it's in the numerator on one side, it's on the denominator on the other side, and vice versa. Okay? Then we read through our second one, and it says, how would the equation change if instead of rate, you measured time taken to travel in a given distance? So here we're going to say distance is constant. again, I'm going to start off with d of A over T of A. Yes, that's exactly what we're doing, is doing it with time. So now we're going to say divided by T of B. And again, everything on the right-hand side is going to remain the same. So you've got molar mass of B divided by molar mass of A. Well, if your distance is remaining constant, those cancel out. And what that means is you have a fraction divided by a fraction. 1 divided by TA divided by 1 divided by TB. So when you divide a fraction by a fraction, you're taking it and multiplying it by the reciprocal. So it becomes T of B over T of A. Hopefully you caught that math that I did. Make sure you take a second and absorb that. So you've got that equation on the right-hand side. That's our second one. And the key here to notice is that if it's in the numerator on the left-hand side, it's in the numerator on the right-hand side, and same with the denominator. So those are our three formulas that we're going to end up using for Graham's law of effusion or diffusion. And we can start with some examples, but before we do, let's just kind of reiterate what we said, that this is an example of just a graph showing us that if you have something that's really lightweight like hydrogen, it's not going to take much time to travel the same distance as it would something that's much heavier like sulfur dioxide. So again, your lighter weight gases travel quicker, your heavier gases travel slower. First question, it says compute the ratio of your effusion and diffusion rates of gaseous ammonia to gaseous hydrogen chloride. So we're looking for a ratio. We just want to figure out those rates. We're looking at trying to compare ammonia and gaseous hydrogen chloride, just hydrochloric acid that's in a gas form. So if we're looking at ratio, we would say the rate of one divided by the rate of the other. It gives us ammonia first, asking us for that ratio of ammonia to HCl. So I'm going to set it up like this. Molar mass. Hey, which molar mass should go on top? Which substance? HCl. Good. So that's the important part, is making sure. Doesn't really matter. Actually, this time I guess it did, because it wanted me to compare ammonia to hydrogen chloride. But making sure that you get that set up correctly to where they're opposite of one another. So now when we start plugging this in, our rate of NH3 divided by our rate, I guess I didn't need to rewrite this, that is going to be equal to our molar mass of HCl, so we just add that up, 35.45 plus 1.01. There we go. That's going to be in grams per mole. I'll write it this time here. And then we do the same thing. I messed that. No, I didn't. Okay, so we've got our HCl there. NH3 is 17.04. That's in grams per mole. So you see that those are going to cancel out. We're going to end up looking for a ratio, just a number. So you don't really need to write those units there within your problem, but just in case you're curious. Now, everybody should plug that in. Make sure you can do the math on something like this. And then check yourself. Make sure you got that. All right, so the question is compute the ratio. So there's a couple different ways that you can really report this. First of all, which one's traveling faster, the ammonia or the hydrochloric acid? The ammonia is traveling faster. That's what it's saying. So not only is it traveling faster, it's traveling 1.46 times as fast. So if it says compute the ratio, lots of times people will write it like this or like that. I'm not going to get real hung up on that. Make sure that you understand which gas is traveling faster, and it's traveling 1.46 times as fast. So that's when you're just calculating that ratio or the rate, trying to figure that out. Okay, next couple questions. And this first one here It says find the molar mass of an unknown gas. So this is our unknown. If it takes 94 seconds required for this unknown gas to escape from an infusion apparatus, but only 54 seconds are required to travel that same distance, right? Similar conditions for neon. So this is the time, 54 seconds is how long it takes neon to travel. So when we set this up, we're going to set it up saying time of one divided by time of another. It does not matter. Just choose one. Someone call one out. Start with unknown. Neon. So neon on top, unknown on bottom, doesn't matter. You're going to see sometimes, though, that the math might be easier in some directions than the other. But so we've got that. Now when we set this up, we've got our molar masses. Hey, what molar mass needs to go in the numerator? The unknown, the neon. Well, I'm not doing very well today. Okay, so neon and unknown goes in the bottom. So if you look back at those that you just, the derivations that you guys just went through, again, it was the time that you notice that they're the same in the numerator and in the denominator. So those don't change. So now you can just start plugging some things in. Time for neon was 54 seconds. Time for our unknown is 94 seconds. That's going to be equal to the molar mass of neon, which is 20.18 grams per mole, divided by the molar mass of your unknown. And I am going to pause this because everybody is going to take some time to really plug this into their calculators. Okay, good. We got an answer of 61.1, and to make it full credit here, that's going to be grams per mole. That's molar mass that we're looking for. So maybe we should have written that here to show that. As far as significant figures go, let's stick with our sig figs. There's 3 sig figs. I know that we say let's go ahead and round our molar masses to 2 past the decimal. That's really more when you grab it off the periodic table. That's how you should use it. But I would stick with the fact that you have 3 sig figs given to you in your problem, so that's what you should use in your answer. Okay, good. Last one. Here we have an unknown gas that diffuses this distance. Well, that's for the unknown. In the same amount of time that it takes ammonia to diffuse this distance. We want to find the molar mass of our unknown gas. So again, we set it up. What do you guys want to choose for the top one? Which gas? Which one? Ammonia. Okay, let's do ammonia. Ammonia on top, unknown on the bottom. Molar mass, molar mass. Well, what does that mean? Which molar mass goes on top? The unknown, because this is the diagonal one. So this one's unknown. And we have ammonia down here on the bottom. Convince yourself of that. Just double check back with all of these derivations that we did and make sure you see that when we're doing distance, you've got the catty corner diagonal thing going. Okay, so we've got this, so we can start plugging numbers in. Distance for our ammonia is 83.9 centimeters. Distance for our unknown is 37.2 centimeters. Molar mass of our unknown, that's what we're solving for. Molar mass of ammonia, you know, is 17.04 grams per mole. So again, it's just a math problem. All right, we just got an answer, and it is 86.7 grams per mole. That's all we've got. Hopefully this makes sense to you guys.